Hello, good evening, everybody. Welcome to a new microscope. I don't know if it's the first time for you guys coming for the microscope. Can you raise your hand if it's your first time? Oh, that's a lot of people. Yeah, me too. But this is not the first time we do this, so you should come more often. Microscope started as an initiative by the employees on Schibsted Classified Media. Schibsted what, you would say? Well, Schibsted is it's a company about classified ads. So if you have heard of Mil Anuncios, Segunda Mano, Fotocasa, or so on, that's Schibsted Classified Media. So started like that as an initiative from the employees, and then after its success, initial success, the company decided to sponsor it. So this is why we have a fancy place to do it instead of a garage underground, pretty crappy, with water. We're going to have some drinks, beer maybe? Yeah, beer later on. So I'm not presenting. I'm just a silly guy who is talking before the guys who are presenting, the talkers. So Galo and Guillermo are going to talk. You have a really easy to type hashtag to do your comments, rants, or whatever. Is TikToks or SCH Tech Talks. And one last thing before that, since we are being sponsored by Schibsted, our company, I must tell you that we are hiring. It's an amazing place to work. Yeah, and yada, yada, yada. Drink a beer with us. We can talk about that later. You will see how cool is working there. And that's the corporate stuff. So now I will leave you with these guys, which are less corporate than me. And let's get it on. Okay. Yeah.
Sí, ¿se oye? Sí. Hello, so my name is Galo. I'm an engineer at Schibsted, as we know. I'm working on the engineering productivity team with Guillermo. Yeah, I've been working for most of my professional life on the JVM, which may be good or bad. But we are going to talk about memory management on the JVM. I'll talk about the agenda before starting. Yeah, so we'll see what it is about. And you present yourself later or now?
You just present it.
Okay, so good.
Gracias.
¿Yo le doy? Bueno, sí. Okay, so the agenda is going to be basically this. We are going to assume that most of you have some basic Java or JVM knowledge. You know what this is about. You have written some Java. You know what the garbage collector is, etc. If you don't, or you need some context about something, just stop and we'll explain a bit better. We will see a few slides on how would you understand your application's workload or footprint in terms of memory usage. That's looking at some tools, the output of some of those tools, and how would you interpret that output. And then I will talk a bit on some techniques to improve that, and Guillermo will especially focus on some more advanced techniques that you can do, not necessarily to improve the performance, but some trade-offs that you can make when you really need to squash your memory usage patterns. You will have to pay something in exchange, but if memory is important, then this is the kind of things that you will want to do. Okay, so one of the main advantages, I'm actually going to move here so you can see something. One of the main advantages of the JVM and Java in general, Java and in general. Should I change the? Yeah. Yeah. Oops. Okay. So one of the advantages of using the JVM and Java and in general the JVM is the ability to. Well, the JVM can do very fast allocation and release of memory, even faster than C and C++. It does. And it can optimize your memory usage on runtime. Those are things that are usually very valuable for developers because they are complex things that you don't need to worry about when you're writing your application. The JVM will do it for you. But at the same time, if you leave it unchecked, you may have some problems, especially, or what you usually see on Java applications is big latency spikes. So you have response times that are more or less like this, and then suddenly they go up. Or a lot of jitter, so it goes something like that. And also you have high memory footprint. All the data that you're storing in memory is going to be fatter than it would be if you were using C++ or C or other languages. This is JStat. It's one of the tools that comes with any JDK. It this is going to fall, with the JDK, and it shows what is more or less a healthy application, or what a healthy JVM would be behaving as. What you can see in here, this you can get this with JStatGC and the PID. I forgot to put that. And you see a number of columns. These two are survivor spaces. The C is the capacity, and the U is the utilization. This is the Eden. That's the old generation, and the other ones we don't care about now. So what the JVM is doing here is assuming the generational hypothesis, which, as you know, says that we assume that most of the objects are going to be very short-lived. So we will behave as if that was true. What is happening in this case is precisely that. You can see that the capacity and the utilization and the Eden, the utilization is going up and then suddenly goes down to 0. It goes up again, goes down to 0, goes up again, etc. That means that the application is allocating memory for objects. Those are not used anymore, so the garbage collector comes and removes them, and that keeps happening constantly. If you look at the old generation utilization, it doesn't change. What this means is that all of the objects that we are creating as the application works are very short-lived. So this is validating the generational hypothesis. We are not going to look into garbage collection tuning, but this is the kind of pattern that you should look for when you tune garbage collection. Size the Eden generation in such a way that you can fit all of the short-lived objects that happen regularly, and they don't need to get promoted to the old generation. That's generally a good thing, because whenever objects go to the old generation, they will pile up in there for a long time, and eventually they will have to get garbage collected. That garbage collecting on the old generation is more expensive than on the Eden. So in general, you want something that looks like this. Another way that you can use to analyze your application memory usage is on GC logs. These kind of options, probably these or a superset of these, should be enabled in all JVMs. It doesn't have that much overhead. We'll give you output like this. I'm not sure that you can see from the bottom, but this is going to be on the internet. What you can see here are several ages. So every time that there's a garbage collection on the Eden, you know that an object gains an age. So these are objects that are successfully or staying alive after a few garbage collections on the Eden. And you can see already here that at age 4, there's a huge number of objects. And then at age 5, they disappear. What this means is simply that the majority of objects that we are creating are staying alive for this period of time, the period of time that takes to do 4 collections on the Eden. This already shows, however, some problems, which you can see here and there. The time to perform this garbage collection has gone to 2 seconds. And this means that we are having pauses on our application that are caused by GC that are stopping completely all the application for 2 seconds. That means that, for example, we are not serving requests to our users. It may not be a problem in a batch application, but it will be if it's a real-time application. And you can see that the main cause for this to happen is on object copy. Object copy, again, I'm assuming that you know that there's 2 survivor spaces. The JVM on the Eden is copying objects from one survivor space to another, then to another, and back and forth. So every time that objects move from H1 to 3, 4, they are being copied from one place to another. If you look at the amount of objects that we are moving, that more or less justifies why you are spending so much time copying objects. You're simply getting memory and moving it back and forth. And this is when generating garbage may become a problem. This shows how you can create a problem by generating garbage. This is a different pattern. I'm not going to explain it that much, but you can see 5 seconds in here. Same cause. Most of it is object copying. This looks a bit different, and the cause is interesting. That's a humongous allocation. In this case, what is happening is that we are having a huge object being allocated on the stack. Huge objects are those that are bigger than half of a region in the G1 collector. That needs to allocate a lot of space. It triggers the garbage collection, and we fall in a similar problem. We need to move a lot of objects from different places to another, from different regions, and that causes a huge pause. GC Viewer is a very useful tool that helps you visualize many of the logs, like the ones that I showed before, in a graphical way. This graph comes from the logs that we showed before. And what you can see, maybe not from the back, something like this. This is requests are starting to appear in here. The application is more or less stable, but as requests start coming, we fill the old generation, which means that objects need to get promoted to the old generation. The hidden stays more or less stable. And at this point, all around this, there's a lot of jitter in the gray line, which is the used size, the used memory in the hidden. This is hard to see. But well, what happens in here, eventually something like this. This more or less recovers. This was because the requests stopped coming. At this point, we start getting requests again, and we enter in the same pattern. There's a lot of objects being moved from one place to another, a lot of objects being promoted to the pink area, which is the old generation. At some point, this thing collapses. The garbage collector creates an application post that is huge. And the application actually died right after that because the garbage collector was consuming all the CPU time and leaving no time for the application. So this is the kind of thing that you may end up seeing in an application that is not managing memory correctly. When you want to examine what are the objects, what is the data that you are creating that is generating these problems, you can use JMap. There's also the possibility of getting a heap dump. The problem is if you're getting a 100 gig heap that is getting full, it's usually not very convenient and not even possible to get a dump of the 100 gig in a server and then ship it back to your laptop so you can open it or not and see what is in there. So typically what you end up doing is getting a histogram like that. And this already tells you usually very valuable information like here. You know what objects are in memory and what objects you have an immense amount of, and you generally know your application, so you know where they may be coming from. This case in particular is interesting because you can see that we have 3 million instances of that JDBC record, and there's also 3 million instances of this and that, longs, array lists, and strings. The one on the top is the histo. This includes both live objects and dead objects. This one is after histo live, which is, it runs a garbage collection and then it reports only the objects that are alive. And here you can see a very clear correlation between the amount of JDBC records and the amount of longs, array lists, strings, and objects and characters. What is happening in here is that you have some object like that. It was actually some object like that. It had a list of objects, timestamp, and strings. We will talk a bit more later about what you can do about this, or what is wrong about that. There is also, when you are trying to understand how your code generates garbage, JMH can be helpful. There's a JC profiler, which you can add on a JMH benchmark like that. And it will generate an output that looks like that. So after on each iteration, it will print the allocation rate normalized, and the churn on different spaces on the heap, as well as the count and the time. So this is telling you how much garbage is being, or the rate of garbage that's being generated in your application. You usually don't want to do this with a whole application. You want to take a small chunk of code that is in the critical path, or is something that is being executed constantly for every single request, and see how much garbage this is generating. This is also useful because it allows you to do capacity planning. If you know how much garbage you are generating per request, you know how much how many requests you can do at the same time that fit in the hidden, and that helps you size the heap. Okay, so I'm going to talk about some best practices first, and then Guillermo will go on the complicated stuff. How's the time? Time?
Son las 7:02.
Okay. Okay, so the first point, or the main point that I would like to highlight is it's very good to consider the cost of our abstractions. As I said before, the JVM helps us by taking some of the complexity away from the developer. You don't need to think about memory management, but that comes at a cost. And the cost is that the JVM and the Java language is wrapping your data with a set some other information that is helping it perform its function. For example, you can look at the code. This is open source, so you can look at what is in the representation of an object on those links. For example, on a 64-bit JDK, you are going to be wrapping every object with an object header that has 16 bytes. On 32-bit, it's 12 bytes. References, arrays, everything that you create on the JVM is usually not going to be the raw data that you need to represent it. It's going to be something else. One of the typical things that may be included in there is how many the monitors that you use for synchronized primitives, etc. One very, very common problem on Java applications is boxing. If you have a long, or you're representing, let's say, a timestamp with a long, and that's what we saw in the garbage collection logs before and the histogram, a long is 8 bytes. In Java, that's 8 bytes plus the object header, that's 16, so we go to 24 bytes. That's 3 times as much data to represent the same thing as you would do in C, in Rust, and in other languages. It can be worse. In the case of a Boolean, which you can represent with a single bit, you actually need 1 byte, and you need the header, and you need 3 bytes for padding, because the JVM will always pad at multiples of 8, I think, or 4, 8. So this goes to 16 bytes. So you're multiplying for 128 the size of your actual data. That's a real-world example. A few years ago, I was doing a system that basically had a cache in memory for whether a song was licensed to play in a given country for a given user that has certain permissions. This could be in Spotify if you're a premium user, or a free user, or an unlimited user, etc. If you calculate all the combinations, if you have a 20 million song catalog, I think Spotify is about 20, 30 million, almost 200 countries and 9 types of permissions, which is a fairly realistic amount, you end up with very huge data sets if you want to represent the whole thing. If you use a Boolean, if you use a flag that is able to represent all this data where each permission is a single bit, then you have a very small data set. It's 34 meg, it fits in 2 laptops, or 1 server, one commodity server that anybody can buy and have. So the point is not so much being very anal about, oh, don't want to use much memory and premature optimization, but these kind of changes are the difference between writing a system that you can run on a single server, and then you have 2 or 3 or 4 instances, but they all have the complete set of data, and you don't need to worry about anything else. You can scale this very quickly, very easily, just by adding servers. If you go to to represent this with a single Boolean, then you need to shard all the data in multiple servers. And the moment that you do that, you're running into distributed systems problems. You need to care about consistency. You need to care about clients knowing to which shard they have to go to find the data, And that is very complicated. So it's not a matter of saving hardware resources. It's a matter of saving developer resources that need to be worrying about this and testing it, designing it, writing it correctly, etc. So one very basic and common recommendation is to do something like that. Every time that you use primitive types, especially, you really need to do that. Use the primitive types. It's going to be smaller, and it's going to avoid all the object header. In Scala, you can use value types, which work more or less something like that, but they are extremely limited. You have the limitations in there. Although they are in some ways pretty useful. You can add the several methods, so you can have an int that has, I don't know, in this case it's a counter, so you have an increment method. And you also need to consider that this is a long, so you have 64 bits in there that are very useful for multiple things. You can pack many things in 64 bits. This thing in here is not going to create more allocations in the general case. And also for Java 10, whenever it comes, will probably be dead by then. Project Valhalla is including value types into Java 10, which will be extremely useful. This is another example of a very fat data model, and this is something you probably won't do in real life, but it's similar, and you can probably get examples, more real examples from here. Here you have a user that has a bunch of fields, a representation of a user with a bunch of fields, and you create the user from a string. This could be a a line separated with all the fields separated by commas. So the typical thing to do is do a split. And here we are separating by double colon. You do the split, you create every object, then you parse it, and then you put each of the fields in the name, in the birth date, This is nice, and it's convenient, and whenever you access all this data, it's there and it's ready for you, and you don't need to construct the data, the date, etc. It has one problem, which is that for every user that you create, you will be creating these many objects. If you have one user, 2 users, 10 million users, 100 million users, and you want to keep those in memory, then this is going to become a huge problem. So yeah, this is pointing here that whenever we cannot afford to multiply the data set sizes, we need to consider if our internal representation of the data, the modeling that we are doing on this subject, on the user, does it really need to map the external contract? So you can do tricks like that, like this. You can have, you can keep the data, the original data, the line of data with all the separators, but do lazy parsing of the data. In this way, whenever somebody accesses the birth date, at that point, only if you didn't parse it before, then you go to this find field method, which simply iterates through the string, finds the correct chunk of data, cuts it, parses that, and returns it to the date. And then at that point you assign it, keep it here, return it, and whenever somebody else comes, it will be there. So it's very basic, lazy initialization, but if you have 5, 7, 10 fields, this is going to save you 5, 7, 10 objects that you may not be accessing on every request. There's a lot more other cases where this is useful, especially hash maps. That's a mistake. On hash codes, whenever you calculate a hash code for something, depending on what you have on the object, for example, you have a list, you're going to go and traverse the list and calculate the hash map, the hash code for every single element, etc. And then you're aggregating all that and then returning the hash code. If the data that you have inside this object is immutable and it doesn't change, you can just cache the hash code and keep it here. Whenever somebody comes and asks for the hash code again, you return the same value. You need to be careful with mutations if they happen, etc. But it's caching this data and lazy calculating is useful. Okay, so Guillermo is taking over. Good luck with this thing.
Okay. Can you hear me? Yeah. So I'm going to focus on techniques you can use to fix your application when basically a set of conditions meet. Okay, you have already fixed all the low-hanging fruit for bad memory management in your application, like things that are just plain bad practices. Okay, you have tuned your GC. You have an application that processes thousands of requests per second and is generating GC on every request. So every time you improve the performance of your application, let's say you are processing 10,000 requests per second, and somebody very smart comes and makes the application twice as fast. Then suddenly, if you were generating 1 kilobyte of garbage in every time you process a request, suddenly you have doubled that amount of garbage, and you have doubled your GC churn, and probably doubled your GC pauses, and increased your latency jitter. Okay, so and your application is sensitive to that. You care about latency. Okay. So in those cases, there are some things you can do that present trade-offs that can make you avoid doing allocations in the fast path of your application. If you do zero allocation in the fast path of your application, basically you should ideally have zero GC pauses. No, you should run without GC. Okay. Okay. So. As I said, these techniques are usually trade-offs, are things that you usually wouldn't naturally do when you program. So they are usually intrusive to your application. So if your application is very latency sensitive and you want it to be high performance, process lots of requests, you probably want to know this upfront and design for it. Okay, and also as a caveat, I would say that before going and optimizing an allocation, you should try to, you should definitely prove that there is a problem there. You should micro-benchmark because some things the JVM does for you. It optimizes things away from it for you, okay? And you shouldn't care about it if that piece of code is not in your fastpath and generating garbage when you process every request. If it's something you do from time to time, or you do an initialization or something like that, it shouldn't be a problem. So it's basically you care about things that are linearly proportional or proportional a function of the number of requests you process. Because as you increase your throughput, you increase your the garbage you have to the GC has to clean up. Okay, so the first case would be objects that you create instantly and you create and throw away instantly. And this, if you program in Java, this happens, or Scala or any JVM language, you know that this happens all the time. There are many APIs that require you to basically do this. Okay. The JVM has an optimization for this. It's called escape allocation, but it's very hard to know when it will kick in. Basically, escape allocation means that it's something the JVM does in the case for which in C++ you would declare something on the stack of a method. Okay, so in C++ you declare something on the stack. Do you use the object, maybe passing it to some other functions, and when you fall out of scope, everything you declare on the stack goes away automatically. So in the JVM, if I create an object inside a function, I use it. I don't give it to anyone else. I don't save it outside of my scope, and my method ends. It doesn't make sense that I would have to allocate that object in the heap and then have the garbage collector do work to free it, because that object could have been freed right there. It could have been allocated in the stack, actually. So since the JVM doesn't do allocations in the stack, it does this escape analysis at runtime, that trying to find out whether an allocation can be optimized away. The only way to know if this is happening is to do a micro-benchmark with that piece of code and really know whether you have to take care of that or not. In case you have such a local variable that you are creating and throwing away, and it's actually creating garbage in every request, what you can do with it is promote it to an instant variable. Very bad programming pattern, I know. And reuse it on every call, and then you would not be making allocations. As I said, these are trade-offs, okay? And you have to be very careful when you do these things with safety. In this case, unless you make the instance variable a thread local, your method will eventually have become thread unsafe, okay? So this is about escape analysis. This would be an example of that case. I think, well, Galo made this slide, so I don't know what the code does. But yeah, this would be the case, for example, okay? The function at the bottom is creating an object, and then it's printing it out, and then it's falling out of scope. So there is no reason why the variable A should be allocated on the heap, okay? The only way to prove that this is happening is to do a micro benchmark. You can also switch on and off the escape analysis when you start your JVM, but I think micro benchmarks are probably much better for this. Okay, another hotspot for in this case are collections. Okay, you may have collections where you put and remove elements as you process requests from your clients, okay? And some of them may be creating garbage, and that's what we are trying to get rid of here, right? So in the case of lists, always use array back lists. Never use linked lists if you can avoid it. So if you use an array list and you size it properly from the beginning, it should probably never need to be resized, and it should never cause any new allocations for your application. If you need to use linked lists or trees, I think the only option is that you build your own intrusive implementations. Intrusive implementations of data structures are those where the pointer to other nodes in the data structure are embedded in your objects. And I haven't researched. I don't think there is a library to do this in Java automatically. So I think you have to really do this every time every time that you would need this, you would need to build your objects with the pointers to build the data structure. In the case of maps and sets, the situation is very bad because maps basically create and sets, which are backed by maps, create a map.entry object every time you insert. So if you have maps that have a lot of churn per request, where you put things and remove them, every time you add an element to the map, you are going to be creating a map.entry, and every time you remove an element, that entry will become garbage. Okay, the only solution to this is to move the maps either off process to a cache like Redis or Memcached, or off heap. Okay, off heap. I will talk about this later. It basically is manually managing your memory outside of the JVM. If you're using queues, again, like list, use them, make them array backed, make them bounded, which also gives you back pressure, which is also a nice design property. And if you're storing primitive types in your collections, be aware that they are boxed when you add them, because Java collections can only store objects. So try to use implementations of collections that are specialized in primitive types and will not make allocations when you insert an int, for example. There are links to them later in the presentation. Actually here. So for primitive types, there is Trove library, and OpenHFT has specialized collections that work on primitive types. Off-heap implementations of maps, also OpenHFT has implementations, and there is a project called MapDB, which has several data structures that are off-heap. Okay. If you want to move your maps off process and put a cache, which maybe could be shared among several processes, like basically a memory caching system, and it could be even off box. Just be aware of one thing: the client library for that caching server should also, if your goal is to not have allocations per request, should also have an implementation that doesn't produce garbage when you try to ask things to the cache. Otherwise, you didn't. You may have one other things, but you didn't help with our goal in this context. In general, if you're using third-party libraries, they may be a source of the garbage we're trying to get rid of, and sometimes you should be ready to either totally scrap them and roll your own, or find other alternatives, or live with that. Another technique is interning. The JVM already does this for some objects. Interning is the act of basically keeping a cache of frequently used immutable objects. Okay, so for example, if we were talking about boxing, but if you try to run a benchmark where you prove boxing and you use byte instances, you will see that they are not creating garbage, because there are only 256 values possible, so the JVM has them cached. The JVM also interns strings. It has a cache of strings. Normally, strings that you create will not be cached. It uses it automatically for things like class names. But you can ask for a string to be interned, and the JVM will keep a copy that it will share forever for the lifetime of your application. Okay. So basically, this is interning consists of a cache of objects that you can query by a key, and you will share a single instance of that object. That's why it has to be immutable for all your application. You can do this for any. You can do this. In which case can you do this? You can do this when the set of possible values of an immutable object is known and unmanageable. If you know how much your interned cache will grow, and you can live with that usage of space, then and you can build those objects based on primitive types to query the cache, then that's a good case for interning. Okay. Again, you're trading space for no allocations. Okay, those objects may not be in use, so you are trading memory footprint for latency, not having GC pauses. Again, a trade-off. Okay, you should consider also making these caches thread local. Otherwise, your interning cache would need to be thread safe, and you would incur in coordination costs when you get objects from your cache, which would again add one more interning cache per thread making it another trade-off of space versus CPU. Another technique is using object pools. So let's say there is a type of object, maybe, I don't know, something that represents your request that you are using all the time in your application and has a complicated lifetime. Like, you don't know when you will stop using it, but at the point that it can be forgotten about, you know. Okay, so in this case, instead of allocating a new object every time, you can have a pool of objects and take objects from there. I think this is a very common, this is not a very weird pattern. People do this in many languages. And you can get objects from there, use them, and when you're done with them, release. Okay, this is a very obvious option to save on allocations. There are a couple of caveats when you do this. One is that it introduces the very real possibility of memory leaks in your application. So if you take an object from the object pool and you fail to release it back into the object pool, you have essentially created a memory leak. So you have introduced memory leaks in Java. Congratulations. Also, if your objects are complicated and they point to other objects, when you release them back into the pool, you should clear them to avoid them sitting in the object pool and pointing to other live objects in the application, keeping them fakely alive. And that would also be a memory leak until somebody comes and takes again that, by chance, that object from the pool and overwrites that pointer. So that's another way of adding a memory leak. Another technique is something I call object stashes, and it's basically a special case of an object pool, okay, which would relieve you from the responsibility of doing the lifecycle management from the objects in the pool, okay? Basically, let's say you have some kind of objects that you are using during your processing of a request, okay, but they don't transcend the request. You know that at the end of the request, they are done. They would be similar to the first case that I mentioned, that are local variables, okay, but they live longer than just one method call, and then they are passed around between several components, and at the end of the call chain, you forget them, okay. So these objects are confined to processing a request. Let's say you have a thread that processes the request end to end. Okay, so you know that all of the objects of this type that the thread allocated when it was processing this request are free whenever the request is done being processed and the thread moves on to process the next request. So in this case, you can have an object pool without lifecycle management. You take objects from the pool, and at the end of processing the request, you tell the pool, hey, I'm done. All of the objects, consider them available again. And you don't have to release objects. You just take objects, forget about them, and at the end of the request, the pool is full again automatically. Okay. So this makes object pools much more convenient if they fit this use case. Again, you should have one of these per thread. This is, by definition, these ones wouldn't work without being per thread. This would be the example, okay? So you have an object, you do some work on it. You have another object, you do some work on the two of them. I would imagine this would not be all in the same method because otherwise it wouldn't make sense. And then at the end of the processing the request, you tell the stash to release all of the objects, and you start over with the next request. Okay. You're still responsible for not leaking objects outside of this request. Otherwise, you would get very weird bugs where objects are being used by two parts of your application with different meanings, okay? And also clearing objects if they point to other data, you could also get weird effects like that. So it's, again, not a very good programming pattern and a trade-off. Okay. Another way of avoiding allocations is basically moving your memory management off heap. Okay, you forget about the garbage collector and the JVM, and you manage the memory on your own. There are two ways to get memory off heap. One is using byte buffers. You can use either byte buffer allocate direct or use a memory map file. That would be a mapped byte buffer. Okay, and then they have an API to put and get values. You can also get slices of byte buffers. They have a very nice API. And the other, this is very frequently used for RPC protocols. Okay. The other is SunMISC unsafe. Has an API to let you allocate memory directly and write and read values from those memory areas. Okay, it will just give you allocate memory will return a long, which is just a pointer. Okay. Okay, so going off heap is related with serialization and deserialization because, for example, if you're using byte buffers, you have memory of heap, but you don't have Java objects on that memory. You have an array of bytes that you need to somehow make sense of. Okay, so there are serialization libraries that are usually used for RPC protocols, but you could also use to store objects of heap that are built with the goal and achieve the goal of having zero allocations. So you can serialize and deserialize objects to and from byte buffers without allocating any memory. Okay, the two of them I'm linking here is one is simple binary encoding. The link is there, and the other one is flat buffers. Okay, they are basically the same. The idea is the same as protobufs or any other RPC definition language and library, but with no allocations. Normally, you have a byte buffer that you manage yourself. You could have a bullet byte buffer, so you could have a huge direct byte buffer and build slices on it, or have a rim buffer, for example. And you tell the library you point it to an area of that memory and tell it to serialize or deserialize a message. Okay, so that would be a byte buffer. And let's say there is a message right there in the middle, so you could, when you call slice on the byte buffer, you basically tell it that you want another byte buffer that only shows you that one record. So you can have many, let's say this is like a flight weight, right? You can have many, a huge area, and then have many, you can pass around build byte buffers that don't overlap the message they should be working on. Okay, and I think that this is it.
Questions?
Yep.
In the wild, so in a company like yours, how hard or how easy do you find when you're coding on a team that needs some tuning to adapt current code, like let's say regular developer, maybe junior or something, into or applying these kind of things? How hard it is, how long it takes?
So, well, I'm fairly new. I'm fairly new to Schibsted, but I've had this in the past where we built up a very large application that was very performance and latency sensitive, and we had our major problem was GC churn and latency at some point. Okay, and it is hard, yeah, because I mean, you know what? First of all, when you start over, you don't know about any of these things. You start thinking about it when you see the problem, and then you look at your system and you know maybe you can. We actually figure out what we had to do in every part of the system to have zero allocations, but the work in a large application to get all of that done would probably be over a year. So it's a long-term effort, but usually the low-hanging fruit gets you massive improvements. It's like everything. But yeah, you can imagine that if you have your application is built with normal Java code that you write casually, or the one that you would write if you don't think your application is performance sensitive. I don't program like this normally. If you want to, if you think about converting that to having zero allocations, it is a very long path, but you can probably get big benefits with moderate effort in many cases.
One thing that After that process, I think one thing I will highlight is the importance of measuring absolutely everything from day one. Sometimes in Schibsted, for example, we are lucky that we are in a situation where we are starting a lot of projects. There's a lot of greenfield projects. So with this experience, one thing that is very important for me is measuring absolutely everything, because it gives you a view of how your application is behaving. You can start seeing if some parts of the application are generating a lot of garbage, and maybe you don't care about them today, but you have that in mind. And you can warn people about that. You can design your application so you can cut a chunk and replace it later. So yeah, I would add that it's very important, not necessarily applying these techniques, but measuring all the time so that you know when you may need to apply them and have that in mind every single day. That's much easier than changing from one day to another.
Yeah, sorry, I have a follow-up question. So basically what you're saying is have performance in mind from day one. So design for performance, more or less, right?
Maybe.
It's like security. You don't add security later, or you don't add quality later. Generally, it's non-functional requirements.
Maybe not necessarily designed for performance, but for example, we were talking a lot about the fast path. So if you're designing something and you know where the fast path is and you know what the pieces of the fast path are, design them properly so you can change them. Because, dumb example, if you get your DTOs, the representation of your DTOs, and you put those in the database, you suddenly have your entire application coupled, and good luck changing the serialization format. If your application is well designed, and that's general good design principles, and the transport and the communication that is doing with other services is isolated and there's a layer and then changes the layer, you can change the serialization format relatively easily. So it's not necessarily thinking about designing for performance from day one, but good design principles, and they leak into the performance benefits later, I think. I would phrase it like that, maybe.
So how do you handle this sometimes called overhead with the product people who are pushing to get features?
Because there's a very simple way. Just get the metrics and translate them into money. That's the only thing you need to do. If you are, for example, and there's a very simple example, there have been a lot of studies already made by Google, Amazon, Facebook, blah, 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 about the impact of 5 milliseconds, 10 milliseconds in the load time of a page. That usually translates into talking to a few microservices, and you're doing serialization, and you're just taking JSON strings and serializing and deserializing in 7 different microservices. There's your argument. The sales are going down. Every time that we make an improvement for 10 milliseconds, sales go up by this. You translate that into money, and then that's it. Sometimes what happens, and that's a problem for engineers, is that the money benefit is not really that big. So it's frustrating for us, but maybe the 10 milliseconds don't translate into the same money that it costs to pay you for a year.
It's not always the case that you need to do this. It's not always the case that you need to go this far and have 0 allocations. It's a very extreme goal to have, but that sometimes makes sense.
I have a question also about object pooling. If you use object pooling, it means that all the objects inside the pool will be treated as in all generation phase. And then it means that my application will grow and grow forever.
For example, yes.
Well, no.
Well, not grow and grow. Sorry.
So I don't imagine you want to be able to handle an infinite amount of data. So you have to have some bounds.
Yes.
Your pool of objects should have a limit.
Yes, of course the object pool has a size.
Yeah.
And I'm talking about if you have peaks of whatever, then it makes those object pools get inflated for a while, and all the objects will be kept inside the old generation. I'm asking more about, for example, proofing. What are the quick wins of those techniques? Because an object pooling, it seems a quick win for something.
It's a trade-off. You're trading latency for memory, because you are going to use more memory, but you are going to have less latency because you're not going to have less GC bosses. That's the trade-off you are making. It's a decision you have to make.
Okay, but for example, latency, of course, is very important for us. And now even more with microservices technology and so on. And it means that every little object that I need, for example, when we were talking about the different stages that we have between isolations. We have the DTOs, and maybe the AP models, version of those objects and so on. It seems that you need an object pool for every layer. And the size of the object pool will be replicated for each layer.
You need an object pool for things that outlive a request, which shouldn't be so many.
Well, okay, you're talking about only the path of the request path.
Well, yes, we are talking only about the request path because that's what the only thing that's proportional to the amount of requests that you process. And I'm talking only of that object pools. It only makes sense for objects that live longer than your request. If by the time you're done processing something, you don't need the object anymore, you don't need an object pool for that because you know there that the object is not needed anymore.
Yes, but I was talking more about, for example, if I have 10,000 requests of the same service, let's say on the same service, it seems that I will use 1,000 times the same object. I can reuse it.
Yeah.
Okay, 1,000 times, let's say. And it seems that object pooling is very useful precisely for this case. Because I'm reusing from one request to another, not inside the same request.
No, that would be the case that I was calling object stashes. Sorry, the terminology is homegrown, but that's not really that. A stash is something that you only use within this request, so it can be much smaller. You are not going in a single request. Let's say you have objects of type foo that you want to reuse. In a single request, you're not going to allocate 1,000 or need 1,000 objects of type foo. You will need a handful. So a stash would only usually contain a handful of objects that you can reuse every time in every request.
Yes, well, I was talking more about not about stash, about the traditional object pooling.
Yeah.
Going across requests, not inside the same request.
One point in there is, and talking related to the design thing. Yes, it is useful that you have a pool and you have 10 threads processing requests and they all go to the same pool and fetch the object and da. Problem that you may find in the future while scaling. At some point, you don't have enough with a machine and you need to move to another machine. It's much easier if you have designed your application in such a way that requests are completely isolated from each other. So every request is a single thread and all the resources they use are their own. That's very good for performance in the concurrency context because they share absolutely nothing. There's no contention between threads. For example, one typical problem with a pool is that you have n threads hammering the pool. And in essence, you have done away with concurrency. You're not having concurrency. If you design the thing so that you have stashes, a number of threads processing requests completely isolated from each other with their own stash of objects, if you want to scale that outside of a single node, it's trivial because you just take one thread or n threads and move them out. And you're managing your application capacity per thread. You know how much capacity a thread can do, how many objects of this type a thread will need to serve a single request, and you can manage those individually. You can move them to another machine, keep them in the same one, etc. And there's no coordination. Whereas going to a single object pool and sharing it, it looks more useful, but in the end, as you start growing the thing, it may not be as useful. Not sure if it makes sense. Yeah. But yeah, you can. There's some cases where you may want to have, for example, a cache. For example, the string data. Well, the string cache when you intern in the JVM, that's a shared instance.
After all these advice about controlling allocation from memory for the JVM and being a Scala aficionado, I'm interested about your opinion about functional programming and immutability. If the JVM is ready, is optimized enough to put this kind of pressure, creating these kind of objects, etc., for a production application. That's quite problem.
No, I mean, I think my view on Scala essentially it's an abstraction layer on top of Java. Every time that you do abstraction layers, you're paying something in exchange. Again, you could write things in C, or you could write things in assembly, and you're trading off. You're making a trade-off. Scala gives you a lot of things, and we actually, at least me, prefer to write Scala in the day-to-day work. But there are parts of the application where you need to be careful about what you do with Scala, and you shouldn't be doing lambdas or etc. Because you can't afford it, because it will start generating closures and da-da.
I was talking about immutability.
Immutability is a similar problem. Like it's very nice and it's very useful, and especially in a concurrency context, it's extremely good. Problem if you are creating a lot of instances all of the time and throwing them away, and every time that you make a copy of a list, that's a common problem in Scala. You add an element to a list, and then you're copying the whole, well, not the whole list, but maybe instances. If you can't afford allocations, then you can't do that, even if it's useful.
I'll say in the case of immutability for functional programming, it really kills me that really most of those objects could be declared on the stack, and you can't do that on the JVM. And I don't think there's a solution for that, because the trick we showed here, this is something that you do exceptionally. You are doing functional programming and you have tons of these cases. It's just your code is going to be unmanageable. So I'm sorry.
More questions? Okay, so thank you all. Thank you very much. I think upstairs we have something to drink. No. Yes? Oh, awesome. I'm sorry. So you go first. Wait for me? No. Yeah. Thank you very much. Thank you, Galo. Thank you, Guillermo. And yeah, let's see you upstairs.